Hello friends, welcome to engineering tutorial. So we'll continue our discussion related to AC circuits. So in this video, we are going to discuss about an important concept which is called as reactance. So in our discussion related to inductive and capacitive circuits, purely inductive and purely capacitive circuits, we briefly touched this topic, but here we'll explain it in detail. Okay, now first let us consider a purely inductive circuit. So we have a circuit, we have an inductor of self-inductance L. It is connected to a AC voltage source. An AC current IT flows through it. Now here let's say the voltage drop across this inductor be VL. So when we apply KVL, we get V minus VL is equal to 0. That implies VL is equal to VT. Let VT, the applied AC voltage source, be represented as Vmax sine omega t. Okay. Now here the induced EMF in the inductor obeys Faraday's law of electromagnetic induction. So this VL is equal to VT. It is given by L dit by dt. Okay, the rate of change of current with respect to time. Okay, the voltage, the induced EMF across the inductor. So here that implies Vt is equal to L dit by dt. That implies dit by dt is equal to Vt by L. That implies dit is equal to Vt by L dt. So we can replace Vt with Vmax sine omega t. That implies dit is equal to Vmax sine omega t dt by L. Now if we want to get the expression of current, we will integrate this. That implies IT is equal to integration of this, so it will be Vmax by L integration of sine omega t. Vmax by L will go outside the integration because it is a constant. So sine omega t. So it will be given by the integration of sine omega t will be Vmax 1 by omega minus cos omega t. Omega is behaves as a constant. We are integrating it with respect to t. Omega behaves as a constant. So 1 by omega integration of sine is minus cos. So we can write it as IT is equal to Vmax by omega L. We can write minus cos omega t as sine omega t minus pi by 2. Why? Because we want to convert both the voltage and current expressions in terms of the sign. okay, sign expression. So here we also did the same thing in our inductive circuits discussion, where the current lagged behind the voltage by pi by 2 radian or 90 degree. Now here the interesting part is this part, omega L part. So here this omega L, this angular frequency multiplied with the self inductance L, this is called as the inductive reactance. This is called as inductive reactance. Okay, now it has a unit of ohms. Okay, unit of ohms. So what inductive reactance does? It provides opposition to the flow of current in the circuit. Okay, it provides opposition. That's why it is in the denominator here. Now it is also expressed as X subscript L, which is equal to omega L. It is called as inductive reactance and has a unit of ohm. Now as you can see, it is frequency dependent in nature. Okay, frequency dependent in nature. That is, we can write the inductive reactance as this omega L, or we can write it as 2 pi Fl, where omega is the angular frequency in radians per second and F is the frequency in hertz. So you can see that here the inductive reactance, it is directly proportional to the angular frequency or directly proportional to the frequency in hertz. So as the angular frequency or the frequency in hertz it will be higher, the inductive reactance will be higher. And if the angular frequency or the frequency in hertz it will be lower, then the inductive reactance will be lower. Okay, this is the concept. So reactance is similar to resistance. It provides opposition to the flow of current. Both of them have the same unit of ohm, but resistance is only for pure resistive circuits. Okay, the opposition provided by resistance, that is for purely resistive circuits. But for inductors and capacitors I will discuss in a separate video. For inductors, the opposition provided to the flow of current in the circuit, it is given by this. XL is equal to omega L, or XL is equal to omega L, which is equal to 2 pi FL, because omega is equal to 2 pi F. Okay, so here the important conclusion that we found is that at high omega or at high F, XL, the inductive reactance is also high, and at low omega or low frequency in hertz frequency, inductive reactance will be low. Now here, when omega will be 0, let's say omega is equal to 0 or F is equal to 0, in that case XL will be equal to 0 into L, so it will be 0 ohm. So 0 ohm means this inductor, it behaves as a short circuit. Omega is equal to 0 or frequency is 0 means for DC supply. So for DC supply, inductor L behaves as a short circuit because XL is equal to omega L or 2 pi FL. As omega is 0 or F is equal to 0, it is 0 ohm. Reactance is 0 ohm. So it behaves as a short circuit. And when omega is equal to very high, let's say infinity, okay, very high frequency. In that case, the inductor here XL will be equal to infinite ohms because frequency is infinity. So in that case, it behaves as an open circuit. No current flows because inductive reactance is infinity. Okay, so at 0 frequency, 0 ohm, short circuit. At high frequency, infinitely high frequency, it is infinite ohm and it is open circuit inductor. Okay, so this is inductive reactance. Next is the complex representation of inductive reactance. So here XL is equal to simply omega L, but when we go for the complex analysis of AC circuits, here this inductive reactance is represented as J omega L, okay, J omega L, where J is equal to root over of -1, J square is equal to -1, iota. J in some cases you will find also I, but mostly in most of the places you will find J, okay, this. So here it goes into the domain of complex analysis, and we'll also discuss in detail how this thing comes. So the inductive reactance, the complex representation of inductive reactance is given by XL is equal to J omega L, and the voltage drop across the inductor, it is given by I XL, which is equal to I into J omega L, or J I omega L. So we can write it as JVL. The voltage drop is in the plus J axis. So here if we try to draw it in complex axis, so here this is real, positive real axis and negative real axis. This is positive, and here it is positive imaginary axis or plus J, and here it is negative imaginary axis minus J. So here let's say current is in the positive real axis, it has no complex representation, the current flowing is this. Voltage drop is plus J I omega L, so it will be somewhere here, okay, this plus J VL. So obviously from here you can see that the voltage drop across the inductor is leading by pi by 2 radian or 90 degree. Okay, it is in the positive imaginary axis, whereas current is in the real axis. So from this also you can determine that for a pure inductor, for a purely inductive circuit, the voltage drop across the inductor, it leads the circuit current by pi by 2 radian or 90 degree, or the current, it lags behind the voltage drop across the inductor by pi by 2 radian or 90 degree. Voltage leads or current lags by pi by 2 radian or 90 degree. So all of it is because of this complex representation of inductive reactance. Okay, so it is called as the concept of inductive reactance, which is similar to resistance because they have the same unit ohm, and their main thing is that they oppose the flow of current through the circuit. Now here another important thing is that this Vmax by omega L or Vmax by XL, it gives us the maximum current Imax. Okay, this. So This is the concept of inductive reactance. Okay.